And now I will turn it over to Mitch, our technical support representative, and he will go over the vibration isolation theory.
Let's jump right in and we'll start with our vibration isolation theory. At the basis of every vibration system, we have three main components. It's going to be some mass, which could be a cab, a computer system, or in this case, we're going to be focusing mainly on an engine system. There's going to be a spring, and there's going to be a damper, and we'll drill down into that spring and the damper portion on these next few slides. If you think of a typical spring, a steel spring, you can pull a spring and it deflects some amount if you apply a certain force to it. And that spring is going to be fairly linear. Apply more force, it stretches more. Elastomeric spring is going to be similar. It's going to have some elastic portion to it where you can apply a force and it deflects. One thing with an elastomer is a little bit different. It's going to also have a nonlinear portion to it. You can apply an excess force and eventually that spring rate is going to become nonlinear. So when we design a system, we typically like to operate within that linear range of the elastomer so the results are more predictable. And as we get more details of an application, we can kind of design the mounts around that. The next item we look at is damping. So damping is the ability, or I guess the property of the system to absorb energy. If you think of a typical shock absorber on a car, it's kind of a basic damper. You hit a pothole, and rather than the car bouncing down the road for several seconds, that damper absorbs a lot of that energy, so you don't feel the input for quite as long. For elastomers and our mounts, the damping is part of the elastomer. So every time you deflect that mount, some of that energy is going to be absorbed in the form of heat. It's called hysteresis damping. And the goal of that damping is to simply absorb some energy so the output is not as great to whatever you're trying to isolate, in this case, an engine system. If we look at this curve here on the right, so you can see the curve, the peak there, that's our resonant frequency. And what damping does, as you increase damping, that peak is going to be rounded off and the output to the system is going to decrease. So when we're sizing mounts for a system, we want to pay attention to where this peak is, and if we can use damping to help bring down that peak so the outputs into the system are not quite as large. When we have a system, think of a simple spring mass. You apply a force to the spring, it's going to oscillate up and down, and it's going to oscillate pretty consistently. That rate at which it oscillates is the natural frequency. We have the two formulas for natural frequency here. On the left, we have the metric formula, which is 1 over 2 pi times the square root of stiffness over mass. And in English units, it is 3.13 times the square root of stiffness over weight. And we use this natural frequency to determine what mounts we should pick to get the best transmissibility for our system. So transmissibility is a ratio of output over input. In any vibration isolation system, we want the output to be as low as possible. That gives us the greatest amount of isolation. And looking at this curve here on the right, you can see that we can shift that curve to the right, but the peak is pretty much always going to be about the same magnitude. So we have a natural frequency, let's say of about 10 hertz, and you can see that peak is all the way up above 10. So that means that at that peak, we're amplifying our input by about 10 times. We can change the mounts, move the curve a little bit left or right, but that peak is always going to be there. So we want to size the mounts so that that peak is outside of our operating range. We want to be on the tail end of that curve where we have the highest amount of isolation.